everyone. So welcome to the online seminar on the mathematical foundation of data science. So our seminar series is generously sponsored by 2 Sigma. So today we are very honored to have a distinguished speaker, Dr. Daniel Kuhn from Epfl. So where he holds the chair of risk analytics and optimization, and he is a professor of operations research at the College of Management. So Daniel Kuhn made fundamental contributions for different fields of optimization and operations research, such as data-driven optimization, robust optimization, and stochastic optimization. So his work is primarily application-driven, and the main application areas are in engineered systems, machine learning, and business analytics and finance. So before joining Epfl, Professor Kuhn was a faculty at Imperial College London, and he did his postdoc at Stanford Management Science and Engineering. And he got his PhD from University of St. Gallen and a master's degree in theoretical physics from ETH Zurich. And currently he is serving as the area editor for continuous optimization for operations research, and he is also associate editor for many top journals like Management Science, Mathematical Programming, Mathematics of Operations Research, and Operations Research Letters. And today, Professor Kuhn will talk about a general framework for optimal data-driven optimization. So please join me in welcoming him. Yeah.
Thank you very much, Ethan, for the kind introduction, and I would like to thank the organizers very much for giving me the opportunity to give this seminar today. So this is actually joint work with my postdoc Tobias Suter and with Bart van Paris from MIT. And in this talk, I would like to propose an approach to construct data-driven decisions for stochastic optimization problems that make, in some sense, the best possible use of the available data. So in some sense, we're going to try to find optimal or efficient estimators for the optimizers and for the optimal values of stochastic optimization problems. And I would like to develop these estimators in a framework that is well-defined, but general enough to capture a broad spectrum of interesting applications. So the framework consists of 3 primitives. So the first one is a stochastic optimization problem, which basically reflects the ground truth against which the estimators we're going to develop will be assessed. The second ingredient is a family of probability measures. So basically the crux of data-driven decision-making is that the probability measure that underlies the stochastic optimization problem is not known, but we're assuming that we have access, so we have some structural information that is captured by a distribution family. And the third ingredient is a stochastic process that generates training samples. So let me first say a few things about the stochastic optimization problem. So you should think of this as a very general stochastic optimization problem, whose objective function we would like to minimize, and the objective function depends on some probability measure that governs the uncertain problem parameters. So examples of the objective function that we'd like to minimize is, for example, the expected loss or the risk of some loss function that is affected by uncertain parameters. Another example would be the conditional expectation of an uncertainty affected loss function given some contextual information. Or a fourth example might be the long run average expected cost of some finitely parameterized control policy. So you see that we adopt here a very general framework, and we just abstractly represent the objective function of this problem by C of x and theta. So as I said, the probability distribution that underlies this stochastic optimization problem is typically not known, but we assume that it's known that belongs to a parametric family. So here, this parametric family or these distributions are encoded by a finite dimensional parameter vector theta, which ranges over a convex set capital theta. And all of these probability measures are assumed to be defined on the same sample space. Okay, and I said, right, so the model space theta over which the parameter ranges is an open and convex set. Now, even though we do not know the true probability measure and therefore the true parameter that encodes the true probability measure, we have access to a finite trajectory of a stochastic process that generates training data, which we can use to actually gain information about theta. So data generating processes that we will study in this talk include, for example, finite state processes, independent and identically distributed random variables, finite state Markov chains, certain classes of vector autoregressive processes, also certain classes of Iid random variables, where each random variable follows the same distribution function, which is from some parametric family, like normal distributions or exponential distributions, etc. So this list is by no means exhaustive. So I would like to emphasize that by developing a framework that also caters for Markov chains and autoregressive processes, we actually do not insist that the training samples we're dealing with are Iid. So we're allowed for serial dependencies. Okay. So actually, throughout the talk, I'm going to use a color coding, and black symbols, they all denote known deterministic quantities. Red symbols, they refer to unobservable quantities, like unobservable probability measures, or the parameters that they encode them. And blue symbols, they encode observable functions of the training samples, of the data. So these are accessible. Now, to make things a bit more concrete, let me give you a simple motivating example. It's the classical news vendor problem, and which really captures the fundamental dilemma faced by the seller of a perishable good. So the textbook example of such a seller is the vendor of newspapers, and of course newspapers, they become worthless at the end of the day. So let me first describe the stochastic optimization problem that the news vendor needs to solve. So at the beginning of the day, the news vendor needs to decide how many newspapers to order from the publisher. So the order quantity is X, and it can be any integer between 1 and D. During the day, then the news vendor faces a random demand, denoted by Xi here, and the demand can also adopt any value, any integer between 1 and D. So the news vendor eventually then tries to find an order quantity that minimizes the expected cost. So the expression of the expected cost is shown here, basically. You see that K represents the wholesale price, and P represents the retail price at which newspapers are sold during the day. So the cost consists of the first term, K times X, which is the cost of ordering newspapers, so ordering cost multiplied by the wholesale price. And then the second term accounts for the profit from sales. So the idea is that the news vendor will continue selling newspapers until either the inventory, X, or the demand, Xi, is exhausted. So the sales quantity is just the minimum of X and Xi. And so the profit is just the sales quantity multiplied by P. So here in this cost is uncertain because the demand is uncertain, and the expectation is evaluated with respect to the distribution of the demand. Now, unfortunately, we do not know this distribution of the demand. However, we assume that we can get some information about the demand distribution from historical demand data. So basically, we assume that we have access to a trajectory, a finite trajectory of demand samples Xi, which are generated by some stochastic process. Now, the stochastic process is governed by a probability measure from within a family that is parameterized by theta. We assume that the true measure is in this family, but we don't know which one it is. And I'm going to make two assumptions in this setting here to make things simple. So let's assume that the demands on different days are independent from each other and identically distributed. And finally, I'm going to assume that the parameter vector theta that encodes the probability measure actually captures the probability mass function of the demand. So the different entries of the vector theta, they just represent the probabilities of the different demand levels. Now, the news vendor would like to solve the stochastic optimization problem on top here. So the news vendor would like to minimize this expected cost function, but this is not possible because the demand distribution is not known. The only thing that is known is a finite sequence of training samples. And as the theta is not known, the news vendor actually should minimize some sort of a surrogate optimization solve a surrogate optimization problem that is not constructed from theta, but is constructed from the data that is accessible. So let me talk about such surrogate optimization models a bit more in general, okay? So as I said, the gold standard is that we would like to solve this original optimization problem, where we minimize the original objective function, which is not accessible because it depends on the model theta that encodes the true probability measure. Now, we should construct a surrogate optimization problem constructed from the training samples. So if you have access to capital T training samples, we can use, for example, some methods of statistics like maximum likelihood estimation to come up with a statistic, theta hat T. And you should think of this statistic basically as an estimator for the unknown parameter theta. And the simplest thing we could do is we could just plug this statistic into the optimization problem instead of theta, and then solve the resulting surrogate optimization problem. Now, of course, this is not the only thing we can do. And in fact, I would argue that we could actually design the whole objective function of the surrogate optimization problem in many, many different ways, not relying on an estimator for theta, but we could use the data directly to build such an objective function. And yeah, I'm going to denote this data-driven objective function just by C hat of t. So how should we construct C hat of t? Well, there is a wide literature on many different approaches how you could do that. Probably the most classical approach is to use the sample average approximation, which evaluates the true objective function just under the empirical distribution of the training data. But actually, we could do something more sophisticated. We could add a regularization term to this empirical risk with the hope to improve out-of-sample performance. Some people, they advocate a predict then optimize approach, which basically just plugs in an estimator for theta into the objective function, which is what I've shown you before. Then this estimator could be trained in view of a generic loss function, like a mean squared error, which is ignorant of the optimization problem we would like to solve, but it could also be trained in view of the actual optimization problem we're interested in. Such things have been proposed, right? We could also just in some way probably train a neural network model to find an approximation of the data-driven approximation of the cost function of our stochastic program. Or we could also use a distribution robust optimization model. So in distribution robust optimization, we basically use the training samples to construct a family of distributions, a set in the space of distributions. And the idea would be that under any distribution, so the observed training samples should be sufficiently likely under every distribution in this ambiguity set, or in this distribution family. And then one would construct the objective function of the surrogate optimization problem as the worst case objective, where the worst case is taken over all distributions in this ambiguity set. And again, there are numerous ways how you could actually design such an ambiguity set. So there are many, many more ways how we could construct a surrogate optimization problem. And really, probably many that nobody has ever thought of that are in principle also possible. Now, just for the rest of the talk, let me introduce some terminology. So I would like to refer to the objective function of the surrogate optimization problem as a data-driven predictor, because it simply just predicts the objective function of a fixed decision X in view of the training data. And of course, this data-driven predictor completely determines the surrogate optimization problem, which tries to minimize this function. Now, I'm going to refer to any minimizer of this surrogate optimization problem as a data-driven prescriptor. And the prescriptor just prescribes a certain decision in view of the data. So it is an estimator for the optimal decision. At this point, I would like to emphasize that the notion of a data-driven prescriptor is extremely general. In fact, you should think of it just as an arbitrary function of the training samples that maps into the space of feasible decisions. Indeed, it's not difficult to see that for any such function, you can find a data-driven predictor that makes the X hat T a minimizer of a surrogate optimization problem. So far, we talk essentially about any data-driven decision as a function that maps the T training samples to a feasible action. So what we would like to do now is we would like to construct this surrogate optimization problem in an optimal way in some sense, right? And actually, to compare different data-driven predictors and prescriptors, I'm going to use 3 different performance measures. So the first one is just the in-sample risk of the prescriptor x hat t, which is just the optimal value of the surrogate optimization problem. So basically, it's the objective function evaluated at a minimizer. And of course, this in-sample risk is accessible to the decision maker because it's simply constructed from the training samples. So this is observable. Now, a second performance measure that is important, of course, is the out-of-sample risk, which basically reports the true objective value of the prescriptor x hat t in the true actual stochastic optimization problem. Now, the out-of-sample risk depends on the parameter theta that encodes the true probability measure, and therefore it is not accessible to the decision maker. Okay. Now, I would like to point out that the in-sample risk per se depends on how we choose our data-driven predictor. And in fact, many different predictors, they lead to the same prescriptor. It's very simple to see, for example, that just if we add just a constant to our predictor c hat t, then this does not change the prescriptor. So this basically tells us that if we try to minimize the in-sample risk, so if we try to construct the surrogate optimization problem with a small in-sample risk, this is nonsensical unless we actually restrict the construction of the predictor, right? And in order to be able to do that, I would like to introduce a third performance measure, which we call the out-of-sample disappointment. So this is just the probability under the unknown true probability measure that the out-of-sample risk strictly exceeds the in-sample risk. So you can imagine that if the out-of-sample disappointment is high, it means that our prediction of the optimal value of our optimization problem is much smaller than the true objective function value of our data-driven decision. And this will basically lull the decision maker in a false sense of security and eventually lead to disappointment in out-of-sample tests. So overall, all of these 3 performance measures, therefore, ideally we would like them to be small, okay? So these are the measures we're going to use to compare different data-driven predictors and prescriptors. Now, at this point, it is important to realize that there is a fundamental trade-off between the in-sample risk and the out-of-sample disappointment. So if you try to make the in-sample risk smaller, and a very simple way to do that would just be to add a negative constant to the predictor c hat t, then invariably you will make the out-of-sample disappointment larger. So you will increase it. And vice versa, right? So there's a trade-off between these 2 quantities, and it's not possible to optimize them. So it should be challenging to optimize them simultaneously, actually. Okay, so I would like to go back to our newsvendor problem now and actually compare different data-driven predictors and prescriptors, or different surrogate optimization problems, in view of these 3 performance measures that we just introduced. So actually, in the left chart, I'm going to show to you how the out-of-sample disappointment evolves as a function of the number of demand samples, the number of training samples, right? In the middle chart, I'm going to show to you how the in-sample risk changes with the number of demand samples. And the rightmost chart visualizes the trade-off between the in-sample risk and the out-of-sample disappointment. So any predictor, any data-driven predictor will be visualized by a point in the plane there, and the x-coordinate represents the exponential decay rate of the out-of-sample disappointment. So this is something we would like to be large. So we would like the out-of-sample disappointment to decay to 0 exponentially at a large rate, because we want the out-of-sample disappointment to be small, right? On the y-axis, I'm going to plot the asymptotic in-sample risk, and that's a quantity that we would like to be small, because it's a risk. So actually, in this experiment, just for information, I'm going to assume that the true demand distribution is such that all demand levels are equally likely. So it's a uniform distribution. The predictors, they don't know that. They just have historical data. So the first model I would like to assess is the sample average approximation model, which just evaluates the expected news vendor loss under the empirical demand distribution, which is or the empirical probability mass function, which is here denoted by theta hat t. Okay, so we can see that the out-of-sample disappointment in this case is roughly at 0.5 for all sample sizes, and that actually can be explained by the central limit theorem. So it does not decay. Actually, the out-of-sample disappointment does not go to zero. On the other hand, the in-sample risk we can see is relatively low, and it saturates very quickly as the number of samples increases. So the brown dot in the right chart visualizes the trade-off between in-sample risk and out-of-sample disappointment. So you can see that because the out-of-sample disappointment does not decay at all, the exponential decay rate is actually zero. Now, if we would like the out-of-sample disappointment to decay, one simple thing we could do is we could add a positive bias term to the empirical objective function. So we could add an R, and if we do that, then we will have a conservative estimator, and that will mean that the out-of-sample disappointment will actually exponentially decay. So if we trace out the R, so if we increase the R, if we sweep the R, then the resulting predictors, they will trace out this dashed line here in the right chart. And as expected, as R is zero, of course, we just recovered the SAA model. But if R increases, of course, we're going to increase the in-sample risk. So that's why the curve goes up. And at the same time, we're going to increase the decay rate of the out-of-sample disappointment. And the curve here shows the trade-off. Now let's look at the second model, or the third model already. That's a distributionally robust optimization model with a moment ambiguity set. So here, I'm going to construct again the empirical demand distribution, and I'm going to evaluate, or I'm going to define my predictor C at T as the worst case expected news vendor loss over all demand distributions theta in this ambiguity set here. So in the ambiguity set, I basically require that the demand distribution of theta matches the first 4 moments of the empirical demand distribution up to some tolerance R. And of course, if I make R bigger, the ambiguity set becomes bigger and the predictor becomes more conservative. Okay, so if the R is chosen relatively small, then you see in green the visualization of what happens. So you see that the out-of-sample disappointment decays roughly at the rate of 2%. The in-sample risk is higher than for SAA, but it saturates also quickly. And the green dot in the right chart shows you asymptotically where this predictor actually is located. If we choose the R a bit bigger, then the asymptotic decay rate, or the out-of-sample disappointment decays faster, as you can see by this more fastly decaying line here. And the in-sample risk, of course, also goes up because we're more conservative. And in the chart on the right-hand side, this predictor here in the limit when t goes to infinity will be located at the light blue dot. Now, as a third example, we could make the R even bigger, and in this case, the out-of-sample disappointment decays even faster, now at the rate of 7% roughly. The in-sample risk gets even higher, okay? And you see this visualized by the dark blue dot. Now, if we sweep R from 0 to plus infinity, or just some positive number, then all these DRO models with the moment ambiguity set, they will trace out this dark dashed blue line here on the right chart, which basically visualizes the trade-off between out-of-sample disappointment and in-sample risk within this family of DRO models. Now, of course, we could construct other DRO models, and actually one that is somewhat popular is a DRO model with a Wasserstein ambiguity set. So here also, we evaluate the worst case expectation of the news vendor loss over a set of distributions. And here actually we look at all distributions that are within a distance R from the empirical demand distribution. And as a distance measure, we use the Wasserstein distance. So we chose a particular radius R for which the out-of-sample disappointment decays as fast as for the moment ambiguity set with a big R, so the dark blue one. And however, we can see that in this case, actually, the in-sample risk is lower. So you see that we get a point in the right panel underneath the blue one. So it dominates the one because it has lower in-sample risk for the same out-of-sample disappointment decay rate. Now, if we sweep the parameter R, then the Wasserstein DRO portfolios that trace out this orange line here in the right panel, as you can see, if R is 0, then the Wasserstein-DRO model just reduces to the SAA model, and of course, therefore, it starts here at the brown dot. And interestingly, actually, the Wasserstein-DRO model dominates the other models at all levels of out-of-sample disappointment. Now let's look at even the fifth model, again, a distribution robust optimization model. And in this case, we use a Kuhlbach-Leibler ambiguity set. So we look at all distributions within a certain distance of at most R to the empirical demand distribution with respect to the Kuhlbach-Leibler divergence. And the first example is visualized here in dark red. So actually for the particular R we chose, the out-of-sample disappointment really decays very fast. The in-sample risk is somewhere lower than other in-sample risks we've seen for other specific examples. And on the right chart, we end up here at this red dot. Now, the interesting thing that happens now is that if we sweep R from 0 to, again, a large positive number or infinity, then the resulting predictors, they trace out this red dashed line here. And again, we have a trade-off, so a higher out-of-sample disappointment decay rate comes at the expense of a higher in-sample risk, but you can see that the trade-off is best here. So the KL DRO model dominates all the other models that we've tested here. So two things to observe in this example. The first one is that actually different data-driven predictors can display very different performance in experiments, as we've seen here. And the other thing I would like to highlight is that actually the out-of-sample disappointment traces out an almost, in all examples, an almost perfect linear function on a log scale as a function of the demand samples. So that really means that if we represent the out-of-sample disappointment by its exponential decay rate, then this decay rate really almost captures perfectly how the out-of-sample disappointment behaves as a function of t. So it's reasonable to look at this exponential decay rate. Okay. So now we've seen this example. Now I would like to try to, in some way, construct surrogate optimization models in an optimal manner. Let's see how we could go about that. Well, actually, the gold standard is to have a low out-of-sample risk. So ideally, we would like to construct a data-driven prescriptor x hat t for which the out-of-sample risk is low. Of course, the out-of-sample risk is always higher than the theoretical minimum, which is just the optimal value of the true stochastic optimization model. Now, I would like to focus on data-driven prescriptors for which the out-of-sample disappointment is small. And that basically means that the in-sample risk exceeds the out-of-sample risk with high probability. And in particular, also, therefore, the expected in-sample risk will exceed the out-of-sample risk with high probability. Now, if we try to construct a predictor, C hat t, which has a low in-sample risk, but we maintain that the out-of-sample disappointment is low, then graphically what we're trying to do is we try to push down the expected in-sample risk. Because the out-of-sample disappointment remains low, implicitly we will therefore also push down the out-of-sample risk, and hopefully we will end up with a good predictor, a good surrogate optimization model. Now, of course, all of this we cannot really do like that because we do not know the theta, right? So the theta represents the true probability measure, it encodes the true probability measure, and this is not known to us. In fact, the out-of-sample risk of the same data-driven prescriptor x hat t can look very different for different probability measures in our distribution family, as shown here. And in fact, we have infinitely many such probability measures, and therefore the out-of-sample risk should really be visualized somehow as a continuous function of theta. And of course, not just the out-of-sample risk, also the theoretical minimum, the optimal value of our stochastic optimization problem depends on the parameter theta of the true stochastic optimization model. Whatever it is, the minimum will change. And also the expected in-sample risk depends on theta because the expectation is taken with respect to the probability measure that corresponds to theta. So if we do not know which theta is the correct one, then one thing we could try to do would be to construct a predictor C hat t that minimizes the expected in-sample risk uniformly for all different theta parameters in the ambiguity set. So if we try to do that and at the same time try to maintain that the out-of-sample disappointment for all theta remains small, and then again, we will graphically try to push down the expected in-sample risk, implicitly will push down the out-of-sample risk, and we will, if we can do that, we'll do that under every possible model theta, and in particular also under the unknown truth theta. Okay, so that's what we ideally would like to achieve. And this motivates us to formulate an optimization problem for designing the best possible predictors and prescriptors. So this optimization problem optimizes over data-driven predictors and prescriptors, which are actually functions of the t-training samples. So this is a very complicated functional optimization problem. Also, we would like to minimize the asymptotic expected in-sample risk of that predictor, but under every possible parameter theta. So this is actually a multi-objective optimization problem with infinitely many objectives. We'd like to minimize the asymptotic in-sample risk under each possible model. Now the constraint here is meant to enforce that the out-of-sample disappointment is small, or more precisely that the exponential decay rate of the out-of-sample disappointment is small. If you ignore the limb soup for a moment and you just multiply the capital T, the sample size to the right-hand side, and take exponentials on both sides, then you basically see that the constraint just asks that the out-of-sample disappointment, which is this probability here, decays asymptotically as e to the minus RT, asymptotically, right? Where T is the sample size, and R is a parameter that we fix. It's like a hyperparameter of our model. So we impose this constraint for every possible theta parameter, okay? So because this is a multi-objective optimization problem, it is not clear that we will actually succeed in finding good decisions. As you might easily imagine, if we try to minimize the expected in-sample risk for one particular choice of the theta, say for theta 1, right? So we try to push this down at theta 1, it is well possible that we cannot simultaneously improve the expected in-sample risk for all other theta as well. In fact, it's possible that we will deteriorate the in-sample risk and the out-of-sample risk for theta 6, for example, right? So ideally, we would like to minimize the expected in-sample risk simultaneously for all theta. But we should actually be quite lucky to achieve that. If it is possible to do that, so if there is a predictor C hat star that simultaneously minimizes the expected asymptotic in-sample risk for every possible theta, then, well, it would have the smallest possible in-sample risk for all models among all other possible predictors. And then this would actually be a so-called Pareto-dominant solution of our meta-optimization problem. And usually this doesn't exist, but I mean, we will see later that actually under certain conditions, we can construct exactly such predictors. Okay, so actually our optimization problem over predictors and prescriptors is essentially optimizing over all surrogate optimization models. So this can be viewed as an optimization problem over optimization problems. And therefore, we actually call this a meta-optimization problem. Now, our formulation has different strengths and weaknesses. So here's the strengths. So on the one hand, this is a proxy for optimizing the out-of-sample risk that does not need access to the true theta. Actually, it's a conservative approximation because you've seen if we keep the out-of-sample disappointment small, we'll actually approximate with the in-sample risk, the out-of-sample risk from above, so from the conservative side. So we err on the side of caution. And that's actually a good thing because it sort of like regularizes the problem and will hopefully also lead to good out-of-sample performance, good generalization properties. Now, I will show you later on that under certain conditions, we can actually find a Pareto-dominant solution for this problem. And this Pareto-dominant solution is even available in closed form. And I've also showed to you that the optimal Pareto-dominant solution leads to some sort of separation between estimation and optimization, which is also very attractive. Possible weaknesses is that the two performance criteria we use, so the asymptotic in-sample risk in the objective and the asymptotic decay rate of the out-of-sample disappointment, these are asymptotic. However, we've seen in the example that actually the out-of-sample disappointment was almost a perfect straight line. So actually, it's maybe not so bad, right? In practice, and the in-sample risk saturated very quickly. So maybe these approximations going to asymptotics is not so bad. You could argue that the choice of this parameter R, which is the target decay rate of the out-of-sample disappointment, is maybe subjective. That is true, but this is like a hyperparameter, like a regularization parameter that also sometimes is subjectively chosen. In this case, the benefit is that it has a precise statistical interpretation. It is really the decay rate of the out-of-sample disappointment, so you really know what it actually means, unlike a regularization parameter otherwise sometimes. You could ask, why do we insist on an exponential decay rate? Why should it not decay differently? We can maybe talk about that later. And another thing is that actually all feasible and optimal surrogate optimization models, they're biased, they're conservatively biased, and that may be perceived as a weakness as well. Well, I would like to show to you that I can actually solve this complicated meta-optimization problem under certain conditions. But before I address the full-blown problem, I would like to address a simpler problem, a restricted meta-optimization problem. Actually, the data-driven predictors and prescriptors, they're just functions of the T training samples. So the number of arguments of these become larger and larger and actually grow with T. And if T is very large, it may be impractical to process or even store these predictors and prescriptors. So it might therefore be useful to actually try to compress the training samples into a summary statistic Theta hat T of constant dimension, and then look at predictors and prescriptors that depend on the data only indirectly through this statistic. Okay, of course we can do that. We can construct such statistics, and here is what will happen with the data-driven predictors. So if they depend on the data only through the statistic, then we obtain much simpler functions. For example, we could construct compressed data-driven predictors, which are encoded by such a function C tilde, which we assume to be continuous. And we could construct compressed data-driven prescriptors, which again depend on the data only through the statistic. And these are captured by a simpler function X tilde, which we assume to be quasi-continuous. This is not so relevant now. So at the bottom here, we see the compressed surrogate optimization problem. Now, focusing on predictors and prescriptors of this compressed form, so that depend on the training samples only through the statistic Theta hat T, this leads to a simpler meta-optimization problem, which is the one shown here. Okay, so this has a much smaller feasible set. Instead of optimizing over all data-driven predictors and prescriptors, very complicated functions, we only optimize over these functions of the statistic. Now, I would like to show to you that this restricted meta-optimization problem admits a predominant solution if the statistic Theta hat T satisfies a large deviation principle. So let me therefore first remind everyone what is a large deviation principle. So we say that the estimators Theta hat T here, they satisfy a large deviation principle if there exists a rate function I such that the inequalities shown here on this slide hold for all possible Borel sets D. Now, first, this rate function here takes two arguments. The first one is a realization of the estimator Theta hat T, and the second one is a parameter theta encoding a probability measure. So you should think of this rate function actually as a distance measure between these two quantities. Now, what do these inequalities here say? Well, on the left-hand side here, we basically have the exponential decay rate of the probability of the event that the estimator falls into the Borel set script. Okay, so in both cases here, right? It links with the limit, but it doesn't make a big difference conceptually. Now, what the first inequality tells us is that the decay rate, the exponential decay rate of this event, the probability of this event here, is at least as large as the distance between theta and the closure of the set D with respect to this rate function, right? And the second inequality tells us that the exponential decay rate of the probability of this event here is at most as large as the distance between the true theta and the interior of the set script D. Okay, so large deviation principle tells us something about the decay rates of atypical events. So on this slide, I show you a visualization to actually clarify things a bit. So the probability simplex here on the left-hand side, you should think of this as the space of all possible realizations of our estimator. Actually, you can think of this as the empirical distribution in our newsvendor problem when we have only 3 different demand levels. So then each estimator realization is just a probability vector with 3 entries. So the red dot here in the middle represents the true demand distribution. Now, what we would like to ask is, let's fix this set D here and let's ask what's the probability that the empirical distribution will fall into this set D. Now it's clear because we have in the newsvendor model, the data are IID. By the law of large numbers, the empirical demand distribution will converge almost surely to the truth, to the theta in the middle, to the red dot. So therefore, the probability of the yellow set D will decay to 0. We're sure about that. However, and the large deviation principle tells us something more. It tells us that the probability of this set D decays exponentially at the rate R, and this rate R is essentially exactly given by the distance between theta and this set, where distance is measured with respect to the rate function I. So this is interesting. These large deviation principles are interesting because actually quite a number of estimators that come up in practical applications, they do satisfy such principles, and we will see that later. Now I come to my first main result. So let us assume that the estimator theta hat t satisfies a large deviation principle and the rate function somehow satisfies some regularity conditions. I don't want to go into details about that. But then we have this first main theorem. So it turns out that under this condition, the restricted meta-optimization problem that only optimizes over compressed data-driven predictors and prescriptors has a Pareto-dominant solution. Moreover, this Pareto-dominant solution has a distributionally robust interpretation. In fact, the optimal compressed predictor, which is shown here, evaluates the worst case objective function over all probability measures encoded by thetas that are satisfying this inequality. So you can think of this as an ambiguity set over all that includes all probability measures whose parameters theta are within a distance of at most r from the estimator theta hat t, and distance is measured with respect to the rate function of the large deviation principle. So the shape of the ambiguity set is really determined by the estimator theta hat t. And actually the radius of the ambiguity set here is exactly given by the decay rate r, which is the threshold that we included in the meta-optimization problem. So that was the target rate. So this is quite nice. And actually, I would like to emphasize that in designing our problem, we had quite some degrees of freedom. For example, when we introduced the distribution family, then we had to specify this parameter space or model space capital theta. And actually, we could have done it in different ways. So actually, we can construct another distribution family by just transforming the original one with some homeomorphism, some coordinate transformation phi. And I'm going to assume that this is a homomorphism. So that means it's a continuous bijection with a continuous inverse. So not only the distribution family, also the estimators could have been defined differently. For example, we could take the original estimator theta hat t and transform it by some function psi to get a new estimator. And again, let's assume that this psi is just a homomorphism. So we can actually prove that our results are invariant under such homomorphic coordinate transformations. In fact, we can show that if the original estimator satisfies a large deviation principle, then also the new estimator will also satisfy a large deviation principle that satisfies the same regularity conditions as the old one. And the new rate function is shown here, determined by the coordinate transformations. And what this actually means that if we apply homomorphic coordinate transformations, then this has actually no impact on how the optimal prescriptor that we find maps the raw data, the training samples, to decisions. So this is actually very good news. So that confirms that we're doing something that is potentially reasonable. So now I would like to go back to the full-blown meta-optimization problem. So far, I've shown you that if you have a statistic, theta hat t, that satisfies the large deviation principle, we can find a Pareto-dominant solution for the restricted meta-optimization problem. I would like to show to you that something similar can be achieved for the full-blown original meta-optimization problem. But in this case, we need an additional assumption on our statistic. Actually, this statistic needs to be sufficient. So here's the definition. We say that a statistic, theta hat t, is a sufficient statistic for the unknown parameter theta if the distribution of the samples psi1 up to psi t conditional on a particular realization of the estimator of the statistic is independent of the parameter theta. And what it actually means is that we have some sort of a lossless compression. So we can actually compress the raw data, the training samples, into this statistic theta hat t. And if I give you theta hat t, then you would actually pay any money for gaining access to the raw data, because any useful statistical information that is contained in the raw data is already contained in the sufficient statistic. Okay, so it seems quite natural. And here basically is our second main result. So let us assume that we have a statistic, theta hat t, that is sufficient. It's a sufficient statistic for the unknown parameter theta. On top of that, like before, we assume that this statistic satisfies a large deviation principle with a regular rate function. So then we come to our second main result, theorem 2 here, which states that under these two conditions, also the full-blown original meta-optimization problem admits a Pareto-dominant solution that again has a distributionally robust interpretation. So in fact, the optimal data-driven predictor, here denoted by C hat t, is given by essentially the same formula as before. So it evaluates the worst case risk over all parameters within a ball of radius r around the statistic theta hat t, where distance is measured with respect to the rate function of the large deviation principle. So this also tells us that there is actually a nice separation of estimation and optimization. So if we would like to evaluate in practice this Pareto-dominant optimal data-driven predictor, the prescriptor, then we can implement two decoupled steps, one estimation step and one optimization step. So in the estimation step, we first take the training data and construct the estimator from them. In the second step, we just plug this estimator into our distribution robust optimization model and solve it. So there's a nice decoupling of estimation and optimization. And the optimal solution, the optimal predictors and prescriptors, they do depend on the data in a simple way, right? Just through this estimator. I would like to point out that this theorem 2 is somewhat reminiscent of a classical result in statistics, which is the Rao-Blackwell theorem. So in our notation, the Rao-Blackwell theorem basically says that if I have an estimator for the objective function of our stochastic optimization problem, so say C hat t here is a data-driven predictor constructed from the samples, which is an estimator for the true objective function. Now, if on top of that we have access to a sufficient statistic for theta, right? Then the Rao-Blackwell theorem tells us that we can actually get an improved estimator by just conditioning the original estimator on this sufficient statistic. This thing here is actually an estimator because it depends, it depends only on the sufficient statistic in the end. Of course, we do not need to have the training samples to evaluate this. Because it's sufficient, even though it seems to depend on the theta, it actually does not depend on theta. So the sufficiency exactly means that this expression here is constant in theta. And what is shown classically is that this new estimator has a smaller mean squared error than the original estimator. So in that sense, it has improved. Now, the proof of this result critically relies on Jensen's inequality, which applies because the mean squared error is a convex risk measure, so to speak, right? Now, unfortunately, so it seems that what we're doing is something similar, right? But in our theorem 2, however, we cannot apply these techniques, these classical techniques at all, because the out-of-sample disappointment, unlike the mean squared error, is not convex in the original estimator. It actually turns out that the proof that leads to theorem 2 is much more complicated than this Rao-Blackwell theorem. But philosophically, there is a close connection between the two things. So in the last part of the talk, I would like to show to you some data generating stochastic processes that actually admit a sufficient statistic that satisfies a large deviation principle. And these are data processes for which we can actually find Pareto-dominant solutions, optimal data-driven predictors and prescriptors, either for the restricted or the original meta-optimization problems, or for both. So as a first example, I would like to go back to our news vendor problem, where we had access to IID demand samples with a finite state space. And in this case, I would like to use as the statistic the empirical distribution, which is a vector of dimension d, and each component just records the empirical frequency of certain demand observations. So it turns out that this empirical distribution is indeed a sufficient statistic for theta that basically follows from the classical Pitman-Koopman-Darmois theorem. On top of that, there is the classical Sarnoff theorem, which tells us that the empirical distribution satisfies a large deviation principle, and the rate function is indeed the Kullback-Leibler divergence from the empirical distribution to the theta. So what this means is that actually we can find a Pareto-dominant solution for our original meta-optimization problem. So we can find a truly an optimal surrogate optimization problem, and that is the one that evaluates that is a distribution robust model with a Kullback-Leibler ambiguity set. Okay, and that's actually one of the models we tested in our experiment, and it was the one that performed best, the one that had the best possible trade-off between asymptotic in-sample risk and asymptotic exponential decay rate of out-of-sample disappointment. So what we know now is that this was no coincidence. We could have tested many more models as well. The Kullback-Leibler divergence would always have dominated all the others, even very complicated ones. We would not have been able to improve that. The second example is finite state Markov chains. So let's assume that Xi is governed by a time homogeneous ergodic Markov chain. And Markov chains are usually encoded by the transition probability matrix. But it turns out that for our purposes, it's more convenient to encode them by the asymptotic doublet distribution. So that's just the joint distribution of two consecutive states of the Markov chain, Xi t and Xi t plus 1, asymptotically as time goes to infinity. And so this leads to a matrix, theta, right? And let's assume here that all one-step transitions are possible. So basically, like shown in the graph, every transition has a strictly positive, though maybe small probability. Now, the set of all such doublet distributions theta is the set capital theta shown at the bottom here. It includes all d by d matrices, which have strictly positive entries because all transitions are possible. The first constraint here just tells us that the sum of all entries should be 1, because it needs to be a probability mass function. And then the last constraint basically tells us that the sum of row I needs to be the same as the sum of column I for each I, and this needs just to be equal to the stationary probability of the Markov chain being in state I. So this is how we encode the Markov chain. Now we need an estimator for the theta, and it makes sense to use the empirical doublet distribution. Theta hat t here, it's also a d by d matrix, and which just records the frequency in our training data set, how often we go from, in one step, from state I to state j. And we calculate the empirical frequency of this. So it's very nice that actually this empirical doublet distribution is again a sufficient statistic for the true doublet distribution of theta. That follows again from the Pitman-Koopman-Darmois theorem. It is also known from the book from Denma and Saituni, for example, that this estimator satisfies a large deviation principle, and the rate function is known in closed form. The rate function is actually the so-called conditional relative entropy, which is shown down here. So that means we can again find Pareto-dominant optimal solutions, both for the original and, of course, the restricted meta-optimization problems. And these are distribution robust problems, and the ambiguity set is here described by the conditional relative entropy. Okay. We can do similar things for certain classes of autoregressive Gaussian processes. For example, processes with unknown drift. In this case, we can use a scaled version of the sample mean to construct a statistic. I'm not giving any details here because I don't have much time. So, but we can show that this estimator satisfies a large deviation principle, but is not sufficient. So in this case, we can actually find a Pareto-dominant solution for the restricted meta-optimization problem, but not for the original one. Another example at the bottom of the slide is again, not a regressive process. In this case, it's a scalar one. And here we assume that the coefficient here is unknown. And this coefficient has several estimators that have been proposed in the literature. One is a simple least squares estimator. Other one is a so-called Yule-Walker estimator. And it turns out both of them satisfy large deviation principles, actually with different rate functions, but they're both not sufficient. So in both cases, we can find Pareto-dominant solutions for the restricted meta optimization problems, but not for the original meta optimization problems. The last example I would like to show to you is that of an Iid stochastic process. So here the observations xi are mutually independent, and each xi follows a distribution that belongs to some parametric family. For example, to the family of normal distributions with unknown mean, the family of exponential distributions with an unknown rate parameter theta, and so on. So you can see geometric distributions with success probability theta, and so on. This list is not complete, so there are many more examples. And what we can show is that the sample mean is a sufficient statistic for all of these unknown parameters in these examples. And actually it satisfies a large deviation principle. That's Kramer's classical result. And the rate function in this case turns out to be the convex conjugate of the log moment generating function of the distribution of one of these observations. So again, we can find Pareto-dominant solutions for all of these examples for the original meta optimization problem. And in fact, we can construct many different uncertainty sets in this way. And you can actually also show them that actually many convex uncertainty sets that have been constructed in the literature or that have come up in the literature, they can be explained in this way, and they're thus optimal for certain classes of Iid processes where certain parameters are unknown. So it's actually quite nice that our theory gives us a way of determining in distribution robust optimization which ambiguity sets are tailored to which kind of structural information we have about our data-driven process. So that's ambiguity sets are so far mostly used in an ad hoc way. And so this really gives some more guidance to modelers. Okay, so I come to the end. I would like to summarize briefly and take some conclusions, and then I will stop immediately. So the main contribution of this work is that we constructed a meta optimization problem for finding optimal surrogate optimization models described by data-driven predictors and prescriptors. So these meta optimization problems, they balance the trade-off between in-sample risk and out-of-sample disappointment. And in doing so, we have seen that they actually push implicitly the out-of-sample risk down. And that is, of course, the ultimate goal that we want to achieve. We want to have low out-of-sample risk. So under some certain conditions, if we have a statistic that is sufficient for the parameter that is unknown and satisfies a large deviation principle, then we have sort of a separation between estimation and optimization. So we can actually solve the restricted meta optimization problem, and we will have the same solution as the original full-blown meta optimization problem. And the optimal predictors can be evaluated separately with an estimation step and an optimization step. So this result is reminiscent of the Rao-Blackwell theorem. And the Pareto-dominant solutions we found, they are distributionally robust models. The ambiguity sets, they are described as balls around the estimator with respect to the rate function of the large deviation principle. And the radius of these ambiguity sets actually reflects exactly the decay rate of the out-of-sample disappointment. So it has a precise statistical information. The results are also invariant on homomorphic transformations. So in some sense, we found through this constructing such Pareto-dominant solutions, we found predictors that are in some sense data efficient. And actually, these predictors we could show are in some sense reminiscent of the classical notion of Bahadur efficiency, which is a bit less known than the efficiency of unbiased estimators that attain the Kramer-Rao bounds. I should emphasize that the results are very general, so they hold even for non-convex decision problems. We've never used any convexity, and they hold also when we've seen examples where the training data is not IID, so serial dependencies are possible. So actually, overall, this gives us some theoretical justification of distribution robust optimization models that have been described in the literature, and gives them a physical interpretation. So I think we didn't talk about computation. It would also be interesting to actually study computational properties of these different ambiguity sets that came up, but that's something that I leave for future work. So with this, I would like to close. I'd like to thank you very much for your interest in this talk. The talk is mainly based on the papers shown here, and the main reference is reference 3 here. Thank you very much for your attention.
Yeah, thank you very much for the great talk. So we have a number of questions. So firstly is, can we guarantee the Pareto dominant solution for the original multi-objective optimization to exist? So the existence of the Pareto dominant solution does it hold in general?
So in general, we do not know whether it exists. And our proofs are constructive because I've shown to you what the Pareto dominant solution is, and we could construct it in case when we, so for the restricted one, it was sufficient just to have a statistic that satisfies that the statistic that we use satisfies a large deviation principle. And for the original one, we needed that this statistic is sufficient for the unknown parameter and also satisfies a large deviation principle. These are the cases we've studied. We do not know what would happen in other situations where we actually cannot construct them. So that we don't know. Yeah.
Okay. Thank you for the answer. So the second question is, so because your approach is mainly based on a parametric approach where we have a parameter, is the generalization to non-parametric method possible, or is it desirable?
So this is a very interesting question. I think, of course, it would be desirable to do that. And it will make things more complicated. So I skipped over many of the technical details. There is lots of subtle issues here because when you talk about these large deviation principles, then you have the, these closures and interiors of the sets come up, and we need a lot to talk about topological properties of the rate functions. Are they continuous? Are they level compact? And so on. And these things are quite difficult to handle. At least for us, it was quite difficult. So therefore, the framework I described is one where we actually could get around these technical difficulties and could actually do it. We believe that actually this theory can be generalized in different ways. And one way would be to non-parametric models. And actually, so we have tried to do this for IID data, and actually that's something that we did in this paper. So there we have, that was an earlier paper where we just looked at IID samples, and we didn't look at sufficient statistics and things like that, so it's a much more restrictive setting. But we managed actually to get some results for IID distributions, continuous IID distributions, where the statistic that we're using is just the empirical distribution. So basically, a discrete distribution on the training samples in an infinite dimensional space of distributions. And in that case, this empirical distribution still satisfies a version of Sarnoff's theorem, and therefore we could still get Pareto dominant solutions in this case, but not more generally. And for sure, it would be very interesting to look into this. Yeah.
Great, thank you for your answer. So the next question is, under which condition will the ambiguity set become the Wasserstein distance bore?
That is also something that we have thought about. And to be honest, so we couldn't really solve it. As a matter of fact, my co-author, Bart van Parijs, so he has a paper, which he just put recently on arXiv a few weeks ago, where he has some connection between this theory and Wasserstein ambiguity sets. So basically, I cannot say much about this because I haven't prepared for this. I think he looks at samples which are somewhat noisy, and there comes something up like an ambiguity set that is reminiscent of a regularized Wasserstein problem, where the regularization is done with a Kullback-Leibler divergence term, something that has been studied a lot also in the theory of optimal transport. And that is the first result that hints at that somehow relates this theory to Wasserstein DRO. But generally, I think this is an open question. I'm not sure whether there is a setting where Wasserstein is optimal. Maybe there is. If there is, it would be interesting, very interesting to know. Yeah.
Okay, thank you for the answer. So the next question is, an audience said, my data are multivariate time series with fat tails. Could you elaborate some light on if and how to apply this framework to process it? So I think basically the question is, if the has some heavy tail distribution, can the method still be applied?
And we don't have any results for this setting. So if you talk about time series, assume you have serial dependence, right? So the only cases with serial dependence that we have studied so far are the ones that I've shown to you. And this is one is the finite state Markov chains, and the other one is the autoregressive processes, but those are for Gaussian noise. So these are Gaussian processes, and they're not fat-tailed. And in principle, there is nothing that I know that would prevent this theory to be somehow applicable to this setting. But the question is always, you need to come up with a large deviation principle. So you need to find an estimate that satisfies an LDP. So I think actually it would be, hopefully this kind of work would motivate statisticians, I myself am an optimizer, to come up with new large deviations principles that exactly for such settings. I do not know. I think in principle this could work if we find a sufficient statistic for the unknown parameters there. But I'm not aware of any such large deviation principle at the moment. Yeah.
Sure. Yeah, and I have a question. So for this framework, can this be generalized to for online algorithms? Because it looks to me that we need to have the whole data to then do the modeling. So this makes the online methods difficult. Do you see any possibility or other approaches to make online methods applicable?
Yeah, again, so this is of course this would be a very nice direction to further look at it. And so we've actually studied. We tried to look a bit at control problems. So we tried to look at LQR control problems, which are the easiest ones. And we have a working paper which is the second one here, right? So we use similar techniques there, where we use actually moderate deviations theory, which is something that is related to large deviations theory. Just that the decay rates that we ask for are not really exponential, but where the speed of the decay can be different. It's actually a bit slower than exponential. So, and we tried to use some of these techniques to find somehow, in a sense, optimal data-driven controllers. Now, to truly do this in an online setting, we have not yet figured out how one could potentially do that. And I will also think that would be that's a very interesting direction to further analyze. But we have some results that we can find, well, such kinds of large or moderate deviations principles that are relevant for optimal control. And we can use them at the moment still in the static setting. We can prove many nice properties. But to really apply them in an online setting, I think that's another step that we still need to go.
Sure. Yeah, that's all questions I have. Yeah, thank you very much for the great talk. Yeah, and look forward to meeting you in person after things come back to normal. Yeah.
Thank you very much. It's very kind of you again to invite me, and thanks for the question and the interest. And yeah, I also hope very much that I can meet all of you very soon at the conference. So yeah, let's hope for the best. Fingers crossed. Thanks.
Yeah, thank you again. Yeah.
Thank you, Daniel. Yeah.
Thank you.
Thank you, Neil.
Yeah. Bye. Yeah, I will. We will see you. Hope to see you again next week. Yeah.
Yeah, sure. Actually, yeah, absolutely.
For the audience. Yeah.